understand that, we have to look at the Earth's eccentricity. And this is a map or a diagram showing the eccentricity of the Earth. That's the shape of the Earth's orbit over the course of 100,000 years into the past and 100,000 years into the future. Now, right now, this is into the past and into the future, so we are right here at 0. And right now, the Earth's eccentricity has a value of 0.0167. So it's a fairly round orbit. Venus's orbit is even rounder, more circular. But you'll notice that the Earth's orbit, the eccentricity changes quite a bit. It's 1.16 now, but there are periods when it's almost up to 0.6. So almost 4 times more elliptical than it is right now. Now, if we look at Venus, displayed on top in red, Venus's orbit right now it's much more circular. It's less than half the eccentricity of Earth's orbit. But there are periods where Venus is more elliptical than the Earth as opposed to less elliptical right now. And you'll notice that the two orbits are coupled together. When Venus goes through an extreme, Earth is at an extreme, at the opposite extreme. So this difference in the changes in the shapes and the ellipticities of the two orbits have important consequences in the number of transits and the duration of the transit cycles that take place. Another factor is Venus's inclination. Over 100,000 years into the past and the future, Venus's inclination, its angle to the Earth's orbit, also changes quite a bit. Right now it's 3.4, but it goes to a low of 1.8 and a high of 4 degrees. So all of these factor into the different periodicities in transit calculations. One question that a lot of people have asked are, is it possible to have a transit of Venus and a transit of Mercury at the same time? And Meus and Vitagliani published a nice paper about 6 years ago on simultaneous transits, and they showed that there was going to be a transit of Venus of Venus and Mercury, but you're going to have to wait until the year 69163. So it's quite a wait. I don't think we're going to make it. Even the young guys in the audience aren't going to make that one. But it's interesting to look at these kind of calculations. The middle example shows a transit of Venus and a solar eclipse taking place at the same time. And that only occurs, just 4,000 years, 5,000 years from now. And a transit of Venus and a solar eclipse taking place, well, that's in the year 15,232. So these are exceptionally rare events where you get a transit taking place during a solar eclipse or two transits taking place. Well, let's get back to some of the history of transits. Edmund Halley, as a young astronomer, traveled to St. Helena in the South Atlantic to study the southern hemisphere and to develop some star catalogs. And while he was there, he took advantage of the fact that there was a transit of Mercury taking place in 1677, and he made some observations of it. And after the transit was over, he noted, on observing this transit, I immediately concluded that the sun's parallax could be duly determined by such observations. Now, in Halley's time, this is another generation after Kepler. They still did not know the absolute scale of the solar system. They only knew the relative distances of the planets with respect to the Earth. But Halley recognized that you could use transits to nail down the actual distances. Well, he thought about this problem for quite a while, and it wasn't until 40 years later that it germinated in the publication in 1716 of an article called A New Method for Determining Parallax. And he published the details of how to do this. It required only a simple telescope and a clock. Didn't take a particularly talented observing skills. But it did require observers to be stationed in vastly different parts of the world, as far away as possible. And he pointed out that the next transit of Venus was in 1761, and he urged, in fact, he challenged the astronomical community to make every effort to go out and try to observe the transit from as many locations as possible. We therefore recommend to the curious investigators to apply themselves to the undertaking of these observations vigorously, because he realized that this was a key to measuring the distance of the sun from the Earth and therefore determining the absolute scale of the solar system. This was the most important scientific, astronomical challenge of the 17th and 18th century. This would be analogous to understanding the origin of the universe in our age. This was the big scientific issue. What is the scale of the solar system? Well, to understand parallax, it's very easy. This is Halley's method. If you have two observers on the Earth at T1 and T2, Venus is located here. Here's the sun. If they observe the transit at the same instant, they will see Venus located at different points on the sun. And using that information, you can calculate this angle alpha here. You know the distance of the two observers because they both have their latitudes and longitudes. And with that information, it's just trigonometry to determine what this distance d is from the Earth to the Venus. You know the relative distance of Venus from the sun and Venus from the Earth. So the rest of it falls into place. You immediately have an absolute measure of everything in the solar system. So during the 17 and 1800s, many countries around the world got involved in almost an international competition of prestige to be the first to measure the scale of the solar system. It was the equivalent of an international space race in the 18th century. And there are lots of different stories about what took place during those different expeditions, but I only have time to talk a little bit about one of the more famous ones, and that was James Cook, who traveled to the South Pacific on the HMS Endeavour. He sailed to Tahiti for the transit of Venus. He was also out to, part of his mission was to explore the South Pacific and to circumnavigate the globe. But his secret mission was actually to try to discover the southern continent, which was still believed to be someplace out there, and he was hoping to claim that land for Great Britain. Anyway, he set up his observations on Tahiti at a location that he named Point Venus. This is a sketch of what Point Venus might have looked like at the time. And this is one of the observing tents with a clock set up. And one of the interesting stories about Cook's expedition was that he was there in Tahiti for a number of weeks preparing for this transit. And of course, he had a lot of sailors on board. And the sailors were getting pretty bored. There was not much to do while they were hanging around Tahiti. There were a lot of very lovely Tahitian women around who were quite willing to render sexual favors for steel nails. They were highly prized. So the ship quickly ran out of stores of steel nails in their coffers, and the sailors began removing nails from the ship. So Cook had to put a stop to that, otherwise they would not get back home. But in any case, they did manage to make successful observations of the transit. But he ran into a problem called the black drop effect. This is what you expect at the beginning of a transit, at the contact, just when Venus is just at the edge of the sun's disk. This is an important time because you can precisely time this position of Venus on the sun. But what you end up seeing is something like this, a blurry image of Venus with sort of a connection to the edge of the sun, sort of a neck to it. I've got a little animation down here. That's what you expect to see, a nice clean break that you can time. But in reality, you end up seeing something like this, where Venus sort of merges with the edge of the sun and it hangs in there. Well, this was a big disappointment. It lowered the precision of the observations. It still allowed you to measure the scale of the solar system, but not as too high a precision as they had hoped. Today, we know that the reason for the black drop is partly due to the atmosphere. It's atmospheric seeing. It's partly due to the size of the telescope you're using, and it's partly due to limb darkening, the dark edge of the sun. It's a contrast effect as you get down to the edge of the sun and the brightness drops off rapidly. So it turned out that using the transit wasn't as good a procedure as they had hoped. 100 years later, photography was now on the scene, this new great tool of astronomy. And astronomers around the world tried to measure the distance to the sun again. But once again, the black drop reared its ugly head and rendered the observations not as precise as they would like. By this point, there were better ways of measuring the distance to the sun from Earth. So the last serious period in the 1800s of these transits sort of ended with astronomers a little disillusioned with the technique. Nevertheless, William Harkness from the Naval Observatory has a very nice quote about transits in the next transit. He said, "There'll be no other transit of Venus till the 21st century of our era has dawned upon the Earth, and the June flowers are in bloom in 2004. When the last transit occurred, the intellectual world was awakening from the slumber of the ages, and that wondrous scientific activity which has led to our present advanced knowledge was just beginning. What will be the state of science when the next transit season arrives, God only knows." So it was interesting to read that quote, especially in 2004 when we were on the verge of our next transit. Here's a quick diagram. This was again a descending node transit in June of 2004. I brought a large group to Greece for the transit, where we had very good weather, but it was a very hot day. The seeing was not very good, and we could very readily see the black drop effect. Here's a composite showing the entire transit. Well, it brings us up to 2012 and the transit next year. Again, it's a descending node transit, but now the Venus passes through the northern hemisphere of the sun. Transit lasts about 6 hours long. And here we see a map showing the visibility of the transit. When the transit begins at Ingress, it's centered almost over Hawaii. North America gets a good view of the eclipse of the transit. Australia sees the beginning of the transit as well. At egress, the end of the transit, Earth is rotated 6 hours, and now Asia and Europe get a chance to see it. If we look at the time of mid-transit, here's ingress, egress, mid-transit, this central area is the place one would like to go to see the entire transit from start to finish. And can be seen a little bit better on this map. The entire transit is visible from this region here. Ingress is only visible on the western side of this diagram, and egress on the eastern side of this diagram. If I shift this a little bit, I just want to point out a couple of mathematically interesting locations. And those are these little orange triangles up in the north and up in the south. In the first case, up here, Iceland happens to be in this little triangular area. What does that mean? It means if you were located in that location, you would see the transit begin just before sunset. The sun would set with the transit in progress, and a short time later, depending on your latitude, maybe an hour or two later, the sun would rise with the transit still in progress. On the other hand, if you were down in the South Antarctic Ocean, you would see the sun rise with the transit in progress. It would only skim the horizon for a short period of time, and then set again with the transit in progress. So just two mathematically interesting locations. This is some weather data from Jay Anderson on the transit. I'm not going to say too much about it. Jay will probably say some more, other than to point out that probably the best locations for weather are the southwestern U.S., northern Australia, and northern Africa, and up into South Asia here. There's an Excel spreadsheet you can download from the NASA website that will allow you to plug in your latitude and longitude, and it'll calculate transits into the future, the visibility of them from any location on Earth. I think I've got this particular spreadsheet has 3,000 years of transits on it. So it quickly calculates the altitude of the sun at every single contact during the transit. So if you want to look at when future transits are going to take place and which part of the world, you can use this as a tool. Well, what kind of science is going to be done at the 2012 transit? Because it's no longer useful from a scientific point of view for measuring the distance of the sun. We've got much better ways of doing that now. Well, there still is a use because the Hubble Space Telescope will be used to observe the transit, but not directly because Hubble can't look at the sun. It would damage the telescope. But what Hubble will do is it will look at the moon during the transit of Venus. And by studying the spectra reflected off the surface of the moon, it will attempt to detect the spectral lines in the atmosphere of Venus. It's a difficult measurement. Very faint signal, but it's important because this is the same kind of an observation you're trying to do when you're trying to measure planets orbiting other stars and trying to detect their atmospheres. So this is an interesting proof of concept to use Hubble to measure the transit in terms of measuring, possibly using it to measure the atmospheres of exoplanets around other stars. Well, you can read all about the transit of Venus in the current issue of Sky and Telescope magazine. Jay Anderson and I have an article in there about the transit. There's also a nice historical article about the 1639 transit in the same issue by Ellie Mayer. And I've also got some information resources on the web, the NASA website, and also Chuck Butler has a very nice website with transit information, transitofvenus.org. A couple of books I recommend are Ellie Maurer's Transit of Venus and Michael Maunder and Patrick Moore's book, Transit, which are great for background information and historical perspective on transits. So I hope that everybody, I'm sure the front two rows, nobody would dare miss the transit. I hope that all the students in the back of the room will catch this too, because it's the only chance in your lifetime to see one of the most remarkable celestial events that has certainly played a pivotal role in the history of astronomy. Thank you.